Hi Katrina, I'm glad you sorted out your issues with partitioning matrices, but I thought I'd take the opportunity to show some basic matrix multiplication calculations and then hopefully show you why partitioning might be useful. So I've created a little example here. We're multiplying a 2 by 2 matrix by another 2 by 2 matrix. So I guess I can write that in there. So the resulting matrix should also be 2 by 2. So when we go about multiplying our two matrices on the left there, we have 4 elements we need to create in our new 2 by 2 matrix. So we do that first. The first element, we take the first row of the first matrix and the first column of the second matrix. So we do 2 times -1 plus 1 times 2. So I'll go ahead and write that in. So it's -2 plus 2. I guess I did a little bit of that in my head. So the same goes for in our resulting matrix here. We have the element in the first row in the second column. So we take the first row of our matrix on the left and we take the second column in our second matrix. So here we go 2 times 3 and plus 1 times 0. So doing that in my head a little bit, that is 6 plus 0. And the same goes for our bottom element. We've got our second row and first column. So we take the second row and the first column, and then we multiply the elements and add them up. So 0 times -1 is 0, plus 1 times 2. So 0 plus 2. And then finally, in our resulting matrix, we have the second row and the second column. So we do the second row and the second column. So we've got 0 times 3 plus 1 times 0, which is 0 plus 0. So I can write that a little bit neater, I guess. And our result is -2 plus 2 equals 0. 6 plus 0 is 6. 0 plus 2 is 2. And 0 in the bottom corner. So that is our result. Okay, so one other, before I get to partitioning the matrices, I just want to talk about a little insight that took me far too long to work out myself, and it's in the hope that it's helpful to someone else. So when we deal with numbers, so for example 3, this is actually a 1 by 1 matrix. So we could also write 3 like that, and it's a 1 by 1 matrix. Another example, not particularly interesting, 2 is also a 1 by 1 matrix. So in the past, when we've done 3 times 2 and got the answer 6, that's the same as having a 1 by 1 matrix with 3 in it multiplied by a 1 by 1 matrix with 2 in it, because the resulting matrix is 1 by 1. And we want to take the first row and the first column, and we do 3 times 2, which is, sorry about the sloppy writing, which is equal to the 1 by 1 matrix of 6. So in this, we can kind of see how matrices are a generalization of what we've always done. All right, so now finally getting on to the partitioning. Okay, so I've now got my new slide, and I'm going to write out the two matrices we had before. We had 2, 1, 0, 1, -1, 3, 2, 0. So with partitioning of matrices, we could actually write this as follows. And that's meant to be a 2, not very well done. So here, we've partitioned our previous matrix into 2 separate segments, and our matrix on the right into 2 separate segments as well. So we can read off here that R1 squiggle, so the squiggle underneath suggests it's a vector, is equal to 2, 1. R2 is equal to 0, 1. And I guess you'll notice that I called them R for row, and then C1 in our second matrix, partition matrix, is equal to 1, 2, and 3, 0. Okay, so noticing that we've still got a 2 by 2 matrix and another 2 by 2 matrix. If we were to do this matrix multiplication with our partition matrices, we still get the same result as before, so I'll just change the colour of my pen here. Our resulting matrix is going to be 2 by 2. So instead of doing my row by column, row by column, row by column, and row by column, we now got our partitioned matrices, but we can still do the same operations. So our first operation for our first element is going to be the first row, which happens to be our R1 vector, and our first column, which happens to be our first column vector. So in here we can write R1 times C1. So for our second element there, which is the first row and the second column, we take our row vector there and our second column, which is that column vector there. So we have R1 times C2. And you probably guessed by now, when we want our bottom left element, that's the second row, first column. So we take that vector times that vector. So we've got row 2. This is starting not to be very legible, my apologies. And then finally for our last element, first row by second column. Oh, second row by second column. All right, so if we went away to work out what R1 times C1 is, we would go this vector times this vector, and would get what we got before, which was 0. We could do the same thing here, so we've got R1 times C2, which is that vector times that vector, and we'll get 6 again, and then repeat the process and we'd get 2 and 0 just like before. So this example, it isn't particularly helpful because it involves more work, but you can envision when the matrices are much bigger than 2 by 2, and maybe they're 10 by 10 or something like that. If we break up our matrices into smaller chunks, we can do lots of sub-calculations using the smaller matrices to get our final matrix. I hope that gives some insight into why you'd want to use partitioned matrices. See ya.